Thank you very much. I have so many notes, so many comments to make following the returning mentors presentations. So I think I'll wait maybe the break for those of you who would like to hear more about it. So I'll keep the OpenMP part going. It's 10 past, so I think it's the right time to get crack it. But yeah, I will have definitely a lot of things to say that I can rely to what they said. So very good talk this morning. So, as always with my slides, I begin by acknowledging the individuals from which I inspire the content that I'm presenting. You can see this as good practice or not, but I will do it. Same with the software that I tend to use, and the license, which basically says you can do more or less everything you want with the slides except changing something in the slides and then making it look like I endorsed your change. So you cannot make my slides say anything you want with my name on it. So, and you will see that these slides, I put this little note now, are designed for live presentation, so they have few notes. Why? Because I'm filling the blanks by talking, compared to the presentations that would be designed for standalone study with a lot of text, but maybe less nice to have as a live presentation. So, the way I designed this workshop is to rely on short units of teaching, where you get roughly a third of the time spent on actual programming. So I show a technique, a new technique, hopefully, well, maybe new technique to you, and then we get an exercise that works this technique in isolation. So it gives a nice step-by-step process with a lot of hands-on. So to begin with, try to scan this QR code. I know it's rare that we invite you to use your phone, but that's one of these times. And then the idea is we're going to see what you already know about this. I'm going to open the poll if I've not already. I think it's already opened, but just to be sure. It's already opened. Just scanning the QR code is not sufficient? You have to give a code. Whoa, interesting. You have to give a code. I've been using that software for like 2 years. I've taught these workshops on 3 continents. I've never had the code thing. So now there's a code. Okay. Oh, got it. Okay. Because the URL was not well made. Okay, my fault then. So if it's the code, it has to be, okay, J, in English, not in French. You swap letters here. GKHZUH. I think if I show that screen here, I'm going to show it here. Yes, let's move this one here up, and this one. Again, created. Fine. Here we are. Because normally with your QR code, you land directly on the server. You don't have to type the code manually. All good for the code? So let's see where we'll get up to now. Fast, slow, okay. That's a great start. Fast and slow, scary, okay. Performance, communication, complicated. Oh, great. The complicated part, yes. OpenMP, multi-threading, distributed memory parallelism, GPU offloading, reverse offloading, all these things are super complicated, especially if you get in nasty details of how to make things super efficient. But my whole job is going to make it look slightly less complicated, even easy. So we'll see if you find that easy at the end. Race conditions, we're going to cover that. Learning, definitely. Telepathy, I cannot help with this one just yet. Telepathy, yeah, no, you have high expectations. Yeah, no. Penguins, why not? Who came up? Nerd, okay, well, and now it's going to go, okay, it's going to go sideways. Fine, okay. I guess it's time for me to... Okay, so what I call the moment of truth. So the moment of truth is log in on Bridges, try to clone the repo, And then in the next couple of slides will consist in taking the first exercise, which contains a basic hello world, compile it and run it. Why? Because if something has to go sideways, it will go sideways now. And I'm not going to let students be in total panic but not daring to say they have a problem until 4 p.m. If we have problems, we take 10 minutes now, we fix it, and then we have everybody on board and we can all move together. So, Bridges 2 is there? No, still not? Okay, that's fine. If you have a laptop with a Linux or Mac, you can easily clone and just get going the same way. You will likely have already everything you need. On Windows, any Windows user, before I get it, yes? Any Windows user who cannot log on Bridges 2? It's a bit trickier for you. You have to download Mobile Xterm or some other things like this. Okay, I'm going to try to cheat a little bit and wait. I'm going to take you to the first exercise because I have maybe some talking to do before, so maybe they'll give just enough time to unlock the Bridges 2 situation. By the way, of course, these slides are available on the Moodle, so you can see everything on the Moodle directly, okay? So the idea for you who can log on Bridges, lucky you, totally jealous, you will find the repository, 2 folders, C and F, for C and Fortran. Everything you will be shown today will be available both in C and Fortran. And then you go in the first exercise. As you will see, the exercises are numbered, right? And we'll just go through them one at a time. And then try to make and run it. If there's something missing, a module or something, it will become visible right now. If you're good to go with this, you're good to go with all the exercises for the entire afternoon. Anyone who can run it, encountering any problem? Something good to know about myself as well. I'm half deaf. On that side, part of the perks of being half deaf is I cannot locate sounds, right? I mean mono, if you want. Meaning, if you ask a question, if you do not give me a visual hint by raising your hand, you will see me desperately looking through the audience to know who's talking because I cannot locate sounds. So, if you want to troll me, that's a good way to do it. Yes? You can log it. Neither of these? Well, you've been banned too. You're part of the lucky ones who have a banned IP. Sorry, because it's really the IP level. It's not the software. Yeah. So all the connection times out means you have a banned IP and it just doesn't treat your request. You should VPN. Yeah, if you can. If the request doesn't come from this IP that has been blocked, if you can somehow circumvent it, VPN should be fine. Sure. And actually, in the topics we're going to cover today, I'm going to have a little talk at first about the motivation and how it works before we get into these 30-minute teaching units and we start to get the codes going. So that may give an extra maybe 20 minutes, half hour. So fingers crossed. Okay, so let's start with this session. Yes, go ahead. Sorry? Oh, okay. We'll have also people in the room who can help you with these issues. So if we have a look, if we try to understand why we're even talking about OpenMP and multi-threading and all these fancy words I've seen, race conditions, performance, parallelism, threads, would someone know in the room, in 1998, we had just broken a barrier of a new frequency record for CPUs. Do you have an idea what it was? 1998. .1 gigahertz, right? So I know you're all laughing now. Remember, at the time we were super proud of ourselves. Within a year, that moved from 0.1 to 1. So times 10 in 1 year. That's pretty good. That gives good news for the future. Actually, things quickly went down from there because to just reach 2 gigahertz, it took 2 years. And 3 gigahertz a year later, but then we had to wait 10 years to get the 4 gigahertz. And then the 5, 2013, so we're like, okay, we're back on track, now we're going to get it. Actually, no, because the 6 gigahertz was just obtained in 2023. So in other words, there's only so much you can boost your raw clock frequency. So it means that we started to think quickly about the idea that maybe since we cannot make our CPUs indefinitely fast, we should learn how to either circumvent the problem and still find a way to make them faster, but we encounter the problem here, which is the heat that you lose is crazy. So that's a big problem in HPC, making sure that the entire supercomputer doesn't go down in flames. That actually is pretty expensive and important. And I cannot go much on this one. I get much further, but it's also there's a current leak as the components become smaller, so we cannot make them indefinitely smaller until someone finds something new here. So we tried instead to increase the number of cores, not making them faster, just using more of them and see where we're up to. If you were talking about multi-threading 25, 30 years ago, 30 plus years ago, you had a problem. Why? Everybody was working on their own library. And it was a problem for everybody. If you were a vendor, you are not able to optimize anything. Why? Because if I spend 3 weeks to sell my new CPU, my new compiler or something, if I optimize your library super well and to death, it's super great, someone is going to come see me with another library 2 weeks later, which I have not optimized at all. So I would have to optimize 300 separate libraries, which is just not doable. And as a user, tough luck. If you're changing your lab, you're also changing the libraries. So everything you have spent is lost. So that was a big problem. So in the 90s, a certain number of people started together and thought we should derive a standard, a single way to do multi-threading that then we can all rely on. And it led to the OpenMP standard. So you can see the ARB, the Architecture Review Board. I know it sounds like OpenMP, yeah, basically it's for you and like 3 people on the planet and you're just having fun between yourselves and that's it. So something I did in 2023, because I'm part of the OpenMP language committee, I just took a screenshot of who was in the building. And it's just a classic weekly meeting, okay? It was nothing special. So for the companies we had that day, okay, the list is always evolving. You can see that there are major players in there, and that's only for the companies. Then if you have a look at the research centers, so I was representing EPCC, but you have NASA, you have then another round with POSI, you have Delaware, you have many universities. So it's not exactly only 3 people having fun between themselves. And this morning, when you had a talk about the top 500, you could see that, yeah, it's definitely there. MPI, OpenMP, 2 standards, more or less created at the same time, have been in HPC for 30 years. There's a reason. They work. We try to get rid of them every now and then, but we can't. They're just really good. So 1997, the version 1 was done. If you want to know what OpenMP is, fundamentally, it's a big PDF. This one is 650 pages. MPI is 1100. Depends on the version, but just big. Major version, but there's still more work. It never stops. Okay, it's been 30 years of evolution, meaning 30 years of optimizations behind the scenes. So what you can use now has been optimized by people for 30 years. This is why it's hard to come up with something brand new and blow OpenMP out of the water, because you would have to compete with 30 years of optimizations. So we're going to see 2 concepts here. It's directive-based, which I'm going to explain, and it follows a forked join pattern, which I'm also going to explain and illustrate. So how it works. In C and Fortran, you have an example here, short piece of code to explain the directive-based approach. So the way it works is, if I free some space so I can put something underneath, I keep the C version, but it's exactly the same for the Fortran. You have first what we call a sentinel in blue, right? Pragma OMP, or in Fortran, $OMP, which tells the compiler, I'm going to give you some specific instructions that are OpenMP instructions. So when you see that, you're going to do some parallelism-related work, which is going to be determined by what I give you after that, after the pragma OMP, which is the name of the directive. It's going to ask the compiler to do a certain type of task. We're going to see the first one right after these slides, which will be how to inject parallelism. After the directive, you have what we call clauses. It's just to give details on how you would like your directive to act. Again, it will be much easier with examples, but just to give you roughly the terms once, so all the maybe annoying stuff is done at first, and then you're good to go. The directive is the whole line, okay? So the directive name, the sentinel, and the clauses, that's the directive. And the associated structured block just underneath between curly brackets, everything together forms a construct, okay? 5 new words, I won't go any further, that's the end of the terminology. Now actual stuff. So, the parallel construct. If you take a hello world, classic hello world in C or Fortran, and you want to parallelize it, that's going to be easy. You drop pragma OMP parallel. That line alone tells the compiler, please spawn threads. The how many I'm going to explain in a second. For now, a number of threads. And every thread will do that code. Okay? What's the code that they should execute? Oh, the one between curly brackets. So you have to give the curly brackets. And that's all that's needed. If you want the Fortran version, same thing. If you struggle to see how that works, basically, in your program at first, you have the main thread, okay, in blue here. When the compiler, when the runtime is going to encounter that parallel construct, it's going to spawn additional threads. So let's assume that in total you want 4 threads. You had your first thread and 3 more threads afterwards, okay? And these 4 threads are going to execute the entire code associated until the end, in this case in C, for example, the closing curly bracket, or in Fortran, the end OMP, okay? It's the closing sentinel, if you'd like. When you reach the end of your parallel region, you get back to single thread execution, okay? Now, parallel, when you switch from the blue arrow to the blue and the 3 red arrows, the parallel block here, that's called forking. And the end of the parallel is called joining. That's the fork join pattern. So it doesn't take much. It's only very few technical terms, but these are concepts. When we'll start to get into the techniques, we may start to get things on a much higher pace. So I wanted to prefer it's really cool and easy at first. Okay. So now, let's say I have parallelized my code, okay, with assuming 4 threads. So what would the output of this program be? If I run this, what do I get in the console? You'd better get it right. Go ahead. Yes. In case, oh yeah, not everybody knows. In case certain students in the room think I'm such a horrible teacher, I put such a pressure on students, it's because David is from EPCC. He did the master's that I did in HPC. He's now doing his PhD in HPC. So I kind of hope he knows that. But he does. Okay. Yes, you're right. It's going to print this hello world 4 times. Why? Because every thread has executed that printf statement. Note, however, let's assume that the first thread, has printed the hello world in the first position. If I run my program again, it may now be the thread that printed in a 4th position. Okay? You may run your program 15 times and get every time different orders in the print statements. That's now something you will have to deal with. The number of threads, I said assuming 4, but you're like, well, yeah, but maybe I have 20 cores, I would like to have 20 threads. or I would not like to use the entire number of cores or something, you can set the number of threads yourself. There's just an environment variable, omp_num_threads. You set it, and then you can move on with your life. You run your program, and every time it will use that number. If you want to change this number for a specific run, yeah, you can put it in line if you want. That makes it easy for scripts, for example. Benchmarking in HPC, we do that a lot. And if you want to change it for a specific parallel region, because you're getting technical now and you're like, the first part of my program, yes, I would like to run it on 32 threads. The second part of my program, I would like to run it on 16 threads. You can change it for a given parallel construct. So if you want an example in C, you just put this clause, that's the first clause we see. So the clause is here to give additional details, bonuses, okay? So in this case, what it gives is OMP parallel, so please give me the parallelism, inject, spawn those threads, but 2, please, or 5, or whatever number you had by default. Okay? For the Fortran programmers, same thing. So yeah, here I was just explaining clearly that yes, if you don't provide num threads, it will rely on the number of threads you have by default. So far, so good? Yes? Again, it's gentle, but okay. Now you may wonder, okay, I have a code, I have my pragma in the code, how do I compile it? Do I need a special compiler for this? So, no, you just take your compiler, now it's all built in. So if you have the new compiler, you just have to pass this additional flag there, fopenmp. If it's Intel, for example, qopenmp. Same for Fortran. Okay, that's pretty simple nowadays. It used to be less simple. 2 functions you're going to need right now. Number 1, when you're going to have multiple threads, how do you know which thread you are? You just have to call this function. And that will tell you if you're thread number 15 or thread number 22 or 304. Simple. You just call this. No arguments, no nothing. And how many threads there are in total? Another function. I know the names are quite similar, but it's such is life. So it's a bit confusing, but it's okay. You'll get over it, I promise. A little something, which is the number 1 trap you'll have for those of you who are really discovering OpenMP for the first time. It's if you try to call OMP get num threads before you created your parallel region, it's going to return 1. Why? Because before you spawn the red arrows, you just have your blue arrow. So you have 1 thread. So if you try to get the number of threads before you spawned the additional threads, you just have 1. So it's going to tell 1. And without spoiling anything, I know a certain Frenchman wearing suits who's known to be sneaky when he designs exercises. So I don't know, me saying this could be helpful in a few minutes, just saying. Now, these are functions, okay, classic good old functions. In C or Fortran, same thing. It's not directive, it's not pragmas, it's just functions, which means you need the include. So in C, openmp.h, and in Fortran, use openmplib, done. Okay? So you put that in your code and you forget about it. Now time for you to have fun. So the way it's going to work is I will give you 6-7 minutes by yourself. If you need help, you can call. And after that, we go step by step and we solve it together. Okay? Okay? I'm half deaf, but if I don't hear anything, I don't move on. Ah, nice. Thank you. Okay. My little issue, well, we'll have someone, because if it's about the code, we're going to do it step by step. It's about logging in. Yeah, because it's being taken care of. So yeah, the connection issues are being taken care of. So I think I'm now part of the lucky ones who can log in, for example. So it's if you still cannot log in, don't worry, it is being resolved as we speak. So it may need some more time. Sorry for that. Okay, So where are we up to with this? So what did you do here to get this one done? Go ahead. Worst case scenario, you say something that's incorrect, but nobody dies. It's okay. Right, okay. I'm being assaulted with pragmas, so that's a good start. Yeah, let's do it there. Pragma OMP parallel. Okay, that's a good start. I don't forget to put my curly brackets. Yeah. Okay. If I run this, I will have a certain number of threads that will print 0, 0. So now I need to get the right values. What? Sorry? Okay. Yeah, I'm likely to make a typo somewhere, especially as I'm now programming this way. So if I make a typo, please tell me, of course. So how do I get my thread ID? That's the hello world of OpenMP. So if you have some OpenMP knowledge, yeah, it may seem super easy. But again, it's because we all progress from start to make sure we don't leave anyone behind. Go ahead. That's the one. And you can easily imagine what's the next question. What, sorry? Yeah. Oh, you got it too. Nice. And now, yeah, if we compile, okay. It's a bit, probably big enough now. Okay, made is fine. I run it. Okay, I have many threads. So, we said if we want to change the number of threads, an easy way to do it is just declaring it before calling it. And now I have 4 threads. Done. What happens is, by default, if you don't give an explicit number of threads to use, the compiler is going to try to find a reasonable number of threads. Well, when you run it actually at the runtime. So if you have 20 cores, likely you're going to have 20 threads by default. Here, clearly we had more than 20 cores available, but that's how it works. Make sense? Yes? Okay, if you're stuck, make sure you say it. Okay, so now that we know how to spawn our threads and how to identify them, oh, of course I can. Is there anyone who tried to call OMP getNum threads before OMP parallel? Let me rephrase. Is there anyone who made the mistake to put OMP getNum threads before parallel and who does not dare to say it? Well, you're just better than me because I definitely did on my first time. So, okay. Okay, I'm the only one making mistakes? Sure. This one? This one. Okay. So you know how to spawn threads. You know how to identify threads, you know how to get the total number of threads, so now you're good to go. You know how big your team is, you know which member of that team you are. Okay, we can get going. Now, what's going to happen is, to these threads, somehow, at some point, they're going to process data, which means we're going to pass variables. Now it begs the question of, how are we going to transfer that variable? Are we going to share it among threads? Or are we going to send a copy to the threads? Are we going to initialize those copies? All these questions are going to be what we are going to focus on right now. If we take a simple example, okay, I have a variable, I want to print its value, I update its value, and I print again the final value, okay? What do you think is going to happen at line 4. What's the value that's going to be printed? Which one, sorry? At line 4, the first print F. Oh, yeah, C and Fortran, different numbers. The first print inside the parallel region, what value is it going to print, you think? 1, 2, 3, yeah, correct. And what's the second print going to print? Who has questions? Four, five, six, correct. What happens is, by default, there's a certain policy that's put in place to share your variable. If you may wonder what these policies are, what we're talking about here, it's these clauses. Shared private, first private, last private, thread private. These are going to determine how your variables are shared. We are definitely not going to cover all 5 today. It's still an introduction, so gentle. We're going to do shared private and first private, and that should get you going for a while. Unless you do something very fancy, thread private, you're not going to use often. But it's good to know. And default none for good practice, definitely. So what happened by reflex, by default, but not by reflex, by default, was that this variable A was passed as shared. And what happens with shared is all your threads are going to access this same instance of that variable. Okay? So when you enter the parallel region, when you have your threads spawning, they all access the same variable. And same when they exit. They all, at the end, leave their modifications. If you want to have a look step by step, let's get back to my little illustration here. I declare a variable, and then when I encounter the parallel, I say shared. What's happening now is every thread in C, you can see it as a pointer, for example, they all get a pointer on the original variable. So any action they do on that variable impacts the original variable. Make sense? Okay. Sure? Okay. So this is how you can use that clause. You just put that little shared parenthesis and the variable name, done. You will see that OpenMP has been designed with really little efforts left on the user side. It's why it's fairly popular with data scientists, for example. You can focus on your field, your expertise, computational chemistry, astrophysics, and the parallelization job, hopefully, doesn't take too much of your time. So OpenMP is a great way to get that done. Of course, they're shared, but there's other approaches. Private. So private does the opposite. Every thread is going to have its own copy, which means, well, there's a subtlety. They will have their own copy, but uninitialized. Okay? Every thread is going to receive a copy uninitialized. As soon as you're inside the parallel region, now you only interact with your copy and that's it. You never touch the original variable. And at the very end, whatever happened to your copy doesn't influence the value that the variable held beforehand. Little step-by-step example. Now my X variable is declared as private. I get inside the parallel region, every thread receives a copy uninitialized. So you can try to print the value. Maybe it will print 0 if your compiler by default initializes everything to 0, or maybe you end up with totally random numbers due to whatever data was at this memory location before. Okay? So every interaction you have is on your copy and your copy alone. You know you have access to the original variable. You can forget it. So now that you know this, what happens in the first print? What's the value that's printed? Who says 1, 2, 3? Who says 4, 5? Yes, sorry? You will say we don't know. So 1, 2, 3, nobody? Who says 4, 5, 6? Okay. Who says we don't know? Who didn't dare to raise the hand, afraid to make a mistake? I have the answer to this already. So it's uninitialized. So in the first print, we just received a copy. We made a copy of that variable, but we haven't initialized it yet. So if we try to print it, I have no idea what we're going to see. What's going to be the value of A after the parallel region? Who says 1, 2, 3? Okay. The second print, the second print at the end. 1, 2, 3? Okay. Who says 4, 5, 6? Okay. Who say we don't know? Okay. So in this case, it will be 1, 2, 3. Why? Because, yes, indeed, you have updated A, but remember, you updated only your copy of A. You never touched the original variable. So everything you've done was contained and never influenced the original variable. So it stays 1, 2, 3. Make sense? Okay. Now, you may be wondering, yes, okay, but what about copies where I actually need the data to be there already when I copy? First private is the third one we're going to cover today. So this one is exactly like private, except that your copies are going to be initialized with whatever value there was in the original variable when you made the copy, and then you're good to go. Okay, these are really fundamental blocks. So if you want the step by step, I declare my variable as first private. Each thread still receives a copy, initialized, yes, but it's still a copy. So anything you do only modifies your copy. So now let's try again. First print, who says 1, 2, 3? Okay. Who says I don't know? Who says 4, 5, 6? Okay. In this case, it's 1, 2, 3. Why? Because that variable A has been passed as first private, so each thread received a copy, but initialized to what value? The value that was in A. Which value was it? 1, 2, 3. Good. Now for the second print. Who says it's 1, 2, 3? Okay. Who says it's 4, 5, 6? Okay. Who says we cannot tell? Okay. It's 1, 2, 3. Remember, we're still talking in terms of copies. They're initialized, yes, but they are still copies. Anything you've done only touched your own copy. Make sense? Yep? Okay. Now this one is for good practice. It's default none. What you've seen is when you don't give shared private or first private, by default, behind the scenes, something happens and effectively your variables are passed as shared, which can be really tricky. So, good tip, please, if you're discovering OpenMP, that's even better because you don't have years and years of routines and habits to modify. Just put default none right now. Why? Because number one, it means you know exactly what's happening. That's good. Two, because if the default behavior, which is to use everything as shared here, changes, you're in deep trouble. And it turns out that OpenMP gave me the best example ever, because tomorrow we're going to see OpenMP for GPU, which also has a default behavior, and that default behavior changed 2 years ago. So everybody who wrote OpenMP codes on GPUs without trying to explicitly list everything had a bad surprise. So yeah, really, I know that if you've been developing in OpenMP for 10 years, it's going to be hard for you to change your coding style, or it's going to take time. If you're just learning, put these 2 words now and be done with it. What that's going to do is, if you don't give explicitly the data sharing attribute clause, that's a long name, the compiler will not even let you compile your program. You will not even be able to produce the executable, because the compiler will tell you, well, you said you were going to tell me exactly how these variables are used, and you didn't tell me if it was shared private, so I'm not compiling. So now you know exactly what's happening. Quick thing, if you want to have multiple variables, you can use commas. Okay, fairly simple, just syntax notation here. You may wonder, what's up with a backslash there? It's when you want to break directives, when you want to use them over multiple lines, because you will see that directives, when you use real-world codes, they get really long because you chain clauses and clauses and clauses. So in C, you can break it with that character. In Fortran, you can break it with the ampersand, and then you need to retype the sentinel, so exclamation mark $OpenMP, and then you can write as many lines as you want. Okay. Well, yes. First, private and shared. Shared means all the threads were going to interact with the original instance of that variable. So anything that a thread does, updating the value, for example, it updates the value of the original variable. First private is every thread has a copy, which means the original variable and its value will never be changed by any of the threads. They have lost this ability. But threads will feel like they're not that outdated. Why? Because the copy they have has been initialized to the original value. So that's the difference. Copies, non-copies, and initialized. Yes? Yes, this is a smart observation as well. There are times where you will be able, if you have a read-only need and you have a big array, you may use it as a shared or first private. Whether threads read from a copy that contains the same value as the original or read from the original, fundamentally, you have the choice. But if it's a big array, you may want to use shared, because if you use first private, I'm going to have to make copies of all these arrays. And you've seen here on the node, when I tried to run the OpenMP code the first time, I had like 256 probably executions. So I had 256 threads. So if you give me a 1 gigabyte array and you use first private and you have 256 threads, you've instantly wasted 256 gigabytes of RAM. One word, that's all it took. So yeah, shared can allow you to save that copy time, for example. Okay, I've talked enough, I need to take a break. So now, time for you to have fun with the hands-on. If you have any question, again, same thing. First, you have 6-7 minutes to do it by yourself, and then we go step by step. Yes?